Like I mentioned yesterday, sorry, I forgot I still had those in. Our chi-square test that we learned yesterday is going to be identical to the one we do today. So mathematically, nothing is going to be different, but the purpose of the test will be different. Okay, and I did put, maybe we'll do a little field trip over to our Canvas page, just so I can show you where I put this calculator reference sheet, which you will potentially find useful to access. Up at the top in class resources and support, I put right here, calculator functions reference PDF. Of course, I did not create this, but it's a wonderful resource I found. And you can see right here, it kind of gives you the keystrokes you need to do in order to find these different functions, what they do, and your input command. So you will not need to worry about the input command as much as far as it'll tell you like what values need to go in which spots, but you're not going to need to input it by hand if you have the most up-to-date operating system, which all of you should have by now. So this is a good resource. So if you forget how to, for instance, access TCDF, you can see second variables distribution. Okay. So that is all well and good. We don't have to spend more time with this. And just as a reminder, that's under the top little module, which is for resources. Let's jump into today's lesson, which will be on independence. All right. Let's remember the whole idea of independence. Oops, I thought there was more to that. There wasn't. So this is actually a slide you guys have seen before. This will hopefully look familiar. You have the probability of A equals the probability of A given B. So if events are independent, then the probability of one event occurring will be the same as the probability of that event, given that another event takes place. So in this case, if we look at a two-way table, the probability of liking dogs is 51. I'm looking at the left one, obviously. The probability of liking dogs is 51 out of 100. So 0.51. It's a probability of, I'll just put D for liking dogs, preferring dogs over cats. Now, the probability for preferring dogs on the condition of being a male is, now we're looking at the conditional probability right here, which is 42 out of 52. And when we get that, 42 out of 52 is definitely not 0.51. That's 0.81. So what we can say is that these are not independent. So knowing that someone is a male, according to this data, knowing that someone is a male is going to give you a pretty big hint of which animal that person will prefer. But if it was independent, then knowing male or female wouldn't give you any kind of extra clue. Okay, now if we look at the next one, the probability of failing a class is 80 out of 200. So the probability of failing is 80 out of 200, which is 0.4. Now let's see the probability of failing given that you're a female. Well, that's 36 out of 90. And if we do that, we get, how about that, 0.4. So these are independent, meaning that the outcome of one does not give us any clue as to what the outcome of the other is going to be. So I can't say like, oh, do you think this random student passed or not? Like, well, tell me, was it male or female? Were they male or female? Oh, it was a male. That doesn't give us anything that we can use to help our decision. All right. So when we were looking at this before, we were just kind of using a general rule. Our general rule, if you remember this, and we didn't have to worry about it too much, but basically, if the percents were within about 3% of each other, we decided that they were independent. So it's like in that last example, we had 0.4 and 0.4. But let's say it was, 0.67 and 0.70, and we're comparing two probabilities. This would be the probability of A. This would be the probability of A given B. And we say, that's close enough. They're probably independent. Now we're going to be a little bit more precise. We're going to be able to use a test to determine, is there independence between these two variables? Okay. So yeah, we saw that passing a particular class, the probability of it was independent of gender. They were equally likely to pass no matter whether they were male or female. Whether a person liked cats or dogs was not independent of gender, since those probabilities were not equal. And remember, the opposite of independent is not independent. We don't say they are dependent. We just say they are not independent. Or if they are independent, because this is going to come into play, then there is no association. If they are not independent, then there is an association. All right, and that's kind of two ways of saying the same thing. The association here means that as one proportion goes up, the other proportion will go up or down. All right. This is the definition from the textbook. You can maybe look at that real quick to see if there's any kind of writing in there that illuminates something for you. But you can see right here, the p-value, the degrees of freedom are given the same way as before. And yeah. So let's just kind of move forward. Now, we were supposed to switch these. Yesterday, we were looking at this idea. If I took two samples on the same variable or more, but if I took two samples on the same variable, I want to test them for homogeneity. Are all these distributions the same? Does this distribution change over time, or does the distribution stay consistent? Independence says, here's one sample and I'm looking at two different variables on it. And if these two variables are independent, or what am I trying to say? We're checking to see that these two variables don't have an association. That's what I'm trying to say. Okay, so here is an example. This might be a little bit of a silly example, but we can still get the idea. We have taco tongue and evil eyebrow, which may be silly names, but basically if you can put your tongue in a loop, if you know what that is, of course, and then I guess evil eyebrow is maybe where you can like raise one eyebrow or something. Is that the evil eyebrow? I don't know. But let's just say, can you do this weird thing with your eyebrows? And if you can, then can you also to make a loop out of your tongue? All right. Now, if this was a normal school year, maybe we'd try and figure out for ourselves, collect some data. But we're going to use the sample data. And there we go. Are we going to calculate this ahead of time? No, let's just run through the process of this. So mathematically, it's the same as yesterday. Our hypotheses will change. And for a chi-square test for independence, the null hypothesis is that there is no association. Wait, is that right? Yeah, okay, good. I want to make sure I didn't lie to you. Independence says that there's no association.
So the null is that it is independent?
The null is that it is independent. Yeah, that's the other way of saying. So that means the alternate is that there is an association, which means they are not independent. Significance level, 0.05. Why not? Okay. And we'll just keep moving forward, but if you need me to stop, get my attention some way. So there's the good thing about these chi-square tests, and I've already mentioned this, is that the hypotheses are always the same. We don't have to examine the scenario to determine what hypothesis to use. We will need to examine the situation to determine which chi-square test is the appropriate one. But once we've determined that, if it's homogeneity, just pick those. Okay. Name of procedure. Oh, it's not the chi-square goodness test for goodness of fit. This is the chi-square test of independence. All right, check conditions. Same as before, this needed to be random. Needs to have the 10% condition met, and it needs to meet the large counts. And we'll see the same thing as yesterday, but let's go back to the prompt. I'll just leave this going for now. Oops. Is this random? Yeah. How do we know? There it is. It's in the prompt. Random sample. So my hope is that the fact that we've gone through this full process a number of times, it's starting to be kind of like, okay, we know what to do. Now we know the next thing to do. So hope you're kind of developing a sort of, I don't know, muscle memory for doing these types of problems. So 10%, did we meet the 10% condition?
Yeah.
We did. Well, we're going to assume that our population, because it just says 600 senior students, it doesn't say from a particular school. Let's assume we're talking about all senior students. Yeah, 600 is less than all seniors.
But if it was talking about a singular school, would you have to rate change? Would it just be about that school?
If it was a particular school, if we didn't have any other information, we could say we have to assume that the sample is less than 10%, though that wouldn't be a safe assumption. I doubt there's 6,000 seniors at a school.
But in that scenario, the school is the population.
Yeah, in that scenario, the school would be. All right, and then large counts. Now, do you remember what we have to do for large counts?
Greater than 5.
Greater than 5. Here's where we have to actually calculate our expected counts. So how do we find the expected counts for this cell right here?
Well, would you assume that the amount of people who do each of these things would be equal?
No. We learned a specific process for this yesterday.
Do you multiply 480 by 200 and then divide by 600?
There it is. You take the row total and the column total, you multiply those together and divide by the table total. So in this case, yeah, 480 times 200 divided by 600. We're going to need these numbers. So go ahead, we can calculate it, the entire table. So I'll just clear this right here, and you guys can go ahead and fill in the numbers. This should be 160, but you guys can fill in the rest. So I wanted to point something out. With this process for finding expected values, what we're doing is we are creating a perfectly independent distribution. because now the probability of liking or being able to do evil eyebrow is 200 out of 600. That's 1/3. Now the probability of being able to do evil eyebrow, given that someone can do taco tongue, is 160 out of 480. That is exactly 1/3. So by doing this expected counts, we are creating a perfectly independent distribution. And from here, we can draw comparisons. We're going to compare one cell to the other. So 180 compared to 160. And we can do our chi-square calculation, which of course is this one right here. Sum of observed minus expected squared all over expected. So we can figure out, is this deviation from expected enough for it to be no longer independent? Because we know what perfect independence would look like for this data set. Okay, now of course I didn't answer the large counts. Did we meet large counts condition? We did, yeah. Our smallest is 40, so 40 is greater than 5, so we're good there. I'd probably put a little more detail if I was asked to check the conditions, but that's good enough, right? For us. So I will, let me see, I won't clear everything. I want to keep these expected counts. Now, the other thing about the 10% condition, I think I've talked about this, but I want to reiterate this point, is there are times when the 10% condition is not necessary. And again, I talked about this yesterday. When that scenario was the person created a die and was rolling it to see if it was a fair die, and we got the results from 90 rolls, that doesn't actually require the 10% condition because there is no, it's not a finite population. There's an infinite number of rolls we could make with that die. So therefore, we just consider each roll independent, and we don't even need to bother with a 10% condition. Okay, I hope to keep making that point clearer. Man, I should have just erased it. I didn't realize it was in a different spot. So 160, 320, 40, and 80. There we go. Now I'll get rid of the rest of this. What a goof. All right, so there we are. We checked our conditions. We're good to go. Here you can see the conditions again. And you can see how we find our expected counts again. So now we can do our specific work, and our specific formula is found on the first page of our AP formula sheet. The sum of the observed value minus the expected squared all over the expected value. So at this point, I'm going to see if you guys can write out the work for this. And well, as you're writing out the work, you can also get started on finding the test statistic and p-value. Keep in mind, you will need to create matrix A in your calculator with your observed values and matrix B in your calculator with the expected. I don't know if I said that right. Observed for A, expected for B. So once you've got that, you can then run your chi-square test. So you can spend time doing all that right now and write on the screen as soon as you feel like you know what you need to write. All right, so there's the test statistic and the p-value. And we're going to do another example. So let me just go ahead and remind you of what your work would look like. This would be 4 different calculations. I have to do one chi-square calculation, well, one calculation right here for each cell. So that would be 4 total. Rather than writing that out and doing it by hand, then what I'm going to do, I'm going to show the first one and the last one. So then my first one would be observed is 180 minus the expected is 160 squared over the expected, which is 160 plus, and then I can put dot, 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 plus, and I can go to the last one. So I'm going to use these values. That would be the observed is 100 plus, sorry, not plus, minus. There it is. Minus 80, which is the expected, squared over 80. And that equals 18.75. And I could even put out front, this my chi-square value equals all those added together. So that's how you can show your work. As far as your picture goes, remember that your chi-square is a weird distribution. This is going to be a degree of freedom of 1. Now, if we didn't know that from the calculator, which it does tell us that on the screen, but if we didn't know that, we can look at the number of rows we have. I have 2 rows. I've got 2 columns. So my degree of freedom is going to equals rows minus 1 times columns minus 1. So in this case, it's going to be 1 times 1. Now, degree of freedom 1, that's important because with this, the degree of freedom, and I exaggerated this, the chi-square distribution looks like that for degrees of freedom 1. And that means I'm going to have a chi-square sitting somewhere over here. I know this doesn't look very good, but it gets a point across. 18.75. I could even show that's at 18.75. And this is the p-value, which is the probability of getting that value or higher. It's always a right-tailed test for this. Okay, are there questions on the work that we did and how to show it? Okay. And underneath all the writing, you can see the degrees of freedom. And now our conclusion. We already know with a p-value that small, we're going to reject the null hypothesis. So just to conclude this one, I'll let you guys do more of it for the next one. Because the p-value is less than our significance level, and here I can do the whatever it was, 1.49 times 10 to the negative 5th is less than 0.05. We reject the null hypothesis. There is convincing evidence and of course this is all kind of formulaic, right? There is convincing evidence that, and this is where I will start looking at the prompt. Do we have convincing evidence that the ability to do the taco tongue and evil eyebrow are associated? We have convincing evidence that the ability to, and I'll just put that much of it, to ... you know, and then associated. So there it is. So I hope this is helpful running through the whole thing. Hope, or maybe it's just as good to know, yeah, we knew what we were doing from the beginning, and that was a waste of time to watch you do the work. So either way, I hope that you're feeling confident with doing this kind of work. And mathematically, like I said, it's exactly the same thing we did yesterday. So that's good to know. So what we're going to do is I have another one right here. In fact, I am not going to worry about going through this step by step. What I want you guys to do is, let me see if I have a specific question. Oh, wait, no, that's not what I'm doing. So I want you guys to start working on this, and I'm going to give you guys a specific question to answer. All right, and I'll have that just written on the screen. I'm not going to go through this step by step. I want you guys to come up with your answer, but you can put on the screen here what you're coming up with when you get to that point. But make sure you're checking your conditions as well and everything else. But there we go. So just to jump in real quick, you can see on the screen I wrote your question you're trying to answer. So in your conclusion, you can answer that particular question. So I think it is safe to say that we met the large counts in order to accomplish this. Of course, it gets a little bit sketchy. Is this 10% and random? We're really looking at a census of everything. And again, this is kind of maybe not the best example for checking conditions, but certainly with the large counts, we could confirm that our smallest category, our smallest cell was still greater than 5. And the other part about this, so this is all looking good. And so I got the same results. The picture, because we have 3 degrees of freedom, which is going to be, this is 4, so that's going to be basically 3 times 1, which gives us 3 degrees of freedom. Okay, because of that, our curve is actually going to have a little bit of a, well, more than a little bit of a curve. And actually, let me do it more like this. So at this point, it's basically down. I thought I erased. Oh, I did erase the other one. Okay, so now we've got whatever, 18.75. Let's say that's right here. That's our chi-square statistic. And it's this right here. And that area is the p-value, which is very small. Smallest one we've seen, perhaps. I think that's the smallest one. Okay, so that's the whole idea behind this. And if we're looking at this, we could make what conclusion? You guys can just verbalize it. I want someone else to say it.
I was just gonna say that yet again we have another example of how America prioritizes the first class, the wealthy, leave everyone else to swim with the fishes. You know, get the rich people out. That's what they did here.
Literally swimming with fishes in this case. Yeah, I mean, preach it, but probably don't answer that way on the AP test.
I think I will.
Okay, go for it. See how it goes.
I'll-
No. Can anyone just verbally say what our conclusion for this should be?
say it right.
It's Friday. It's a perfect time to be bold.
I'm gonna call you out.
Eli, you're being called out by Leo.
I wonder if he's gonna say it again.
I don't know. I'm not sure.
Okay. Here, I can get someone started, whether it's Leo or Eli or anyone else. Because our p-value is, see if you can go from there.
Let's go, Eli.
All right, I'll do it. Because our p-value is less than the significance level of 0.05, we reject the null hypothesis, and our null was, would it be they aren't independent of each other?
The null is that.
Oh no, the
there
null
is
is they aren't. And then so it would be that they are independent, right?
Well, the null is that there is no association,
Oh,
meaning they are independent.
okay. So they aren't independent and there is an association.
There is an association. Yes.
Okay.
So the second part to that, and you had that, you're up to the good start there. Because our p-value is less than our significance level of 0.05, we reject the null hypothesis. There is convincing evidence that survival and passenger class are associated. Okay, so when we reject the null, we determine that there is an association between the two variables. And now maybe we can kind of wrap this up by considering the difference between this being a test of homogeneity and this being a test of independence. So notice this is right here. each person is categorized. So this 212, each one of those numbers is a person, and they're categorized according to two different variables. It's one sample of 2,201. In this case, technically it's a population, but let's say it's a sample. There's one sample of 2,201 people, but they're differentiated according to two variables: what class they were in and whether they survived or died. Now, this is where homogeneity can be a little bit confusing because, well, some of the stuff we looked at yesterday, we were looking at how males and females responded. And so wouldn't male and female be considered just a variable? Well, I will say that a lot of times, maybe not always, but a lot of times, male and female, if it's taken from two different samples, we can consider the male and female to be maybe a test of homogeneity. But if it was one sample and then we're splitting it apart into different variables, then at that point it becomes a test of independence. So it can get tricky sometimes. Luckily, I have some examples. And what I want you to do right now is conclude if we're looking at a test of homogeneity, of goodness of fit, or of independence based on these chi-square tests. So let me go back to one of the early slides here. And then I'll come back, make sure I come back to the correct slide. So we're going to move to slide 24. Somewhere over here. There it was. So if it's one sample and one variable, that's goodness of fit. If it's one sample testing two variables, that's going to be a test of independence. So remember, that's supposed to be switched up here. If it's two samples testing on one variable, that's going to be a homogeneity. So try and ask yourself basically, am I looking at two different samples and I'm comparing them? Or am I looking at one sample that's been split into two different variables? And it's not always going to be straightforward, but let's see if you can figure out in this test. You don't need to answer this, or you don't need to go through and answer the question. I just want you to determine which test are we using. Look at it. So in this case, the big question to ask yourself is, are we looking at two different samples or is it one sample split into two variables? And right here, because it says it's separate random samples, then there we go. I would agree this is a test of homogeneity. That would be my thoughts on it. Okay. So now we can look at this one. Okay, so the consensus so far is that this is a test for independence, and I agree. Now, the one thing that you can immediately narrow it down to is the fact that this is a two-way table. So that's going to tell us it's one of these two. It's not going to be a goodness of fit. And now the reason it's an independence test is because this is just one sample, it's a random sample of adults. And now, based on probably a big questionnaire, lots of different factors that they were asking about, they identified two different variables. What was the education level achieved, and what was their opinion on astrology? So that's one sample with two variables. Therefore, we're going to check to see if those two variables are independent. All right. And there you go. You probably can guess what this one's going to be. Let me clear all the writing. So in this case, they do only give us one variable. It's one sample. Now, you still maybe need to think through it a little bit, because what are we comparing this to exactly? Well, we do have a theoretical probability for what it should come out to. If there's 18 red, 18 black, 2 green, and this is a fair roulette table, we should get this breakdown as far as the spins. Out of 200 spins right here, we should get 18 out of 38. That proportion should be red, black, and then 2 out of 38, that proportion should be green. So we can figure out what the expected count should be, and we would create that and compare those two using goodness of fit. All right. And I will say this, the best thing you can do, there are certain homework problems that are going to be assigned, and of course go through and practice with those. But maybe one of the best things you can do is look at all the questions in the book, and you don't have to do the entire process for every problem, but a lot of them will kind of ask which type of chi-square test should be performed. And just kind of quiz yourself on all of those, because there's a bunch of problems in the chapter in the book. So take your time to do that. And of course, the progress check, which is available for you. At this point, I would recommend spending this weekend going through those 8A and 8B, getting those done. And, come to class on Monday. If you have questions about any of this, then make sure you've got those questions ready to go, and we can get all that taken care of. So with this, you can see your homework right here. It should be available on Canvas, but you can look at that stuff. And if you have any questions, stick around. If you are good to go, you can have a wonderful weekend.